Hello friends, welcome to my lecture on second order PDE with variable coefficients. The second order linear PDEs occur in various physical problems such as the motion of a vibrating string, heat flow, electricity, magnetism and fluid dynamics. Now let us see some physical problems where and see how they occur. So let us say consider the equation Z equal to Fu plus Vv Gv plus W, where F and G are arbitrary functions of u and b respectively, and u, v and w are prescribed functions of x and y. Then you differentiate this equation with respect to x partially, so that you get the derivative of z with respect to x, partial derivative of z with respect to x, which is p equal to f dash u into derivative of u with respect to x, which is ux, plus g dash b into bx plus wx. And when we differentiate this equation partially with respect to y, we get the partial derivative of z with respect to y as q equal to f dash u into uy plus g dash b into vy plus wy. Now we can find the second order partial derivatives. So let us differentiate this equation with respect to x partially. So then the partial derivative of p with respect to x will be r, because p is the partial derivative of z with respect to x. So partial derivative of p with respect to x will be zxx. So then this is a product of two functions of x and y. So we use the product formula for the derivative. So f double dash u into partial derivative of u with respect to x. So you get ux into ux, that is ux square, then f dash u into derivative of ux with respect to x. So you get f dash u into uxx. So this is f dash u into uxx, and g dash b into vx. When we differentiate with respect to x, what we get? G double dash b into bx into bx. So bx square, and then g dash b into bxx, and this wx gives you wxx. And similarly when we differentiate this p with respect to y, what we get? P with respect to y gives you zxy. So s, this is equal to s. Okay. Now zxy will be, you differentiate this equation with respect to y. So f double dash u into uy. So f double dash u into ux uy, and then g double dash b into by. So g double dash b into bx by, and then f dash u into uxy. So f dash u into uxy, g dash b into bxy and wxy. And when we differentiate this equation, q equal to f dash u into uy plus g dash b into by plus wy with respect to y, what we get is zyy. So this is equal to zyy. So we get zyy equal to f double dash u into uy into uy square, g double dash v into by is by square, and then we get f dash u into we had uyy. So f dash u into uyy, g dash b into byy and wyy. So this is how we get the values of r, s and t. Here we are assuming that zxy is equal to zyx. That is the order of differentiation can be interchanged. Now eliminating the arbitrary constants f dash, g dash, f double dash and g double dash from the 5 equations. We have 5 equations here. This is one equation, second equation, third equation, fourth equation, fifth equation. So from these from these 5 equations, let us eliminate the 4 quantities f dash, g dash, f double dash and g double dash. We can write this equation as p minus wx. P minus wx equal to, this can be written as p minus wx minus f dash u minus ux minus g dash b into bx. Okay. And similarly q minus wy, this equation converted as q minus wy equal to f dash u r minus f dash u into uy minus g dash b into by equal to 0. So, so we can write these 5 equations in the known arbitrary functions f dash g dash, f double dash g double dash. Eliminating those 4 quantities f dash g dash, f double dash and g double dash, we arrive at this equation p minus wx ux bx 0 0, q minus wy uy by 0 0 and r minus wx f double. So, here these 0 0 occur because there are no terms containing f double dash and g double dash here in these 2 equations. Here we have the terms in f dash u, g dash u, f double dash u, g double dash v. So, that is why we have here these terms, but here these zeros occur because these 2 equations first 2 equations do not contain f double dash and g double dash. Now, so this is how we come to this determinant equal to 0. Now, which this determinant involves only the partial derivatives p, q, r, s and t and known functions of x and y. W is known to us, u is known to us, they are functions of x and y. So, their partial derivatives ux, bx, uy, by, wx, wy. Then second order derivatives uxx, bxx, uyy, byy, wxx, wxy, uxy, vxy are all known to us. So, so what we do is we expand this determinant by the first column. Okay. So, then what will happen is that when we expand this determinant by the first column, we will have we will have this equation RR plus SS plus TT plus PP plus QQ equal to W, where R, S, T, PQ and W, R, S, T, PQ and W, they are known functions of x and y, and therefore, the relation 1 is a solution of the second order PDE 3. This is your PDE 3 and this is you can see this is a second order partial differential equation, because R is second order derivative of z with respect to x and S is second order partial derivative of z with respect to x y and T is second order derivative of z with respect to y and P is partial derivative of z with respect to x of first order, Q is partial derivative of z with respect to y of first order. So, this is a second order partial differential equation and it has been derived from z equal to fu plus gv plus w. So, we can say that this relation z equal to fu plus gv plus w is a solution of this second order PDE. Now, this PDE is of a particular type because the dependent variable z is not present in this equation. The capital R, capital S, capital T, capital P, capital Q, capital W, they are functions of x and y and rest are partial derivatives r, small s, small t, small p, small q. So, this is a partial differential equation of second order of a special type because the dependent variable z is not present in it. Now, let us take an example. Say suppose we have this relation z equal to f of x plus a y plus g of x minus a y, where f and g are arbitrary functions and a is some given constant. So, then what we do is let us try to find a second order partial differential equation from here. We shall see, we will get a second order partial differential equation when we eliminate the arbitrary functions f and g. So, let us differentiate this equation with respect to x, then we get let me take u equal to x plus a y and v equal to x minus a y. So, then when we differentiate this equation with respect to x, we get f dash u into ux plus g dash b into bx, and this is equal to f dash u. Now u equal to x plus ay, so ux equal to 1, and b equal to x minus ay, so bx equal to 1. So we get f dash u plus g dash b. Now let us differentiate this equation z equal to f x plus ay plus g x minus ay with respect to y. So q equal to partial derivative of z with respect to y, and we get f dash u into uy plus g dash b into by, and what we get uy equal to, now u equal to x plus ay. So uy equal to a and by is equal to minus a. So we get here f dash u minus a times g dash b. Okay, now what we do is let us differentiate this equation p equal to f dash u plus g dash b once more with respect to x. So what we get, partial derivative of p with respect to x will be equal to f double dash u into ux plus g double dash b into bx, and we know ux bx are 1 each. So f double dash u plus g double dash b. Okay, and when we differentiate q equal to f dash u minus a times g dash b once more with respect to y, what we get, and we know this is equal to r is equal to zxx. So partial derivative of p with respect to x, and t is partial derivative of q with respect to y, and this is equal to f double dash u into uy minus a times g double dash b into by. Remember, a is a constant. So now here uy equal to a, okay, and by equal to minus a. So we get a times f double dash u by equal to minus a. So we get a square g double dash here when we differentiated q with respect to here when we differentiated z with respect to y, we got f dash u into uy, and uy equal to a. I have not written a here. So this is a square, okay, a square f double dash u plus a square g double dash b, and this is equal to a square times f double dash u plus g double dash b. Now from this equation and this equation, this one, okay, we can eliminate the arbitrary functions f double dash and g double dash. R is equal to f double dash plus g double dash, t is equal to a square into f double dash plus g double dash. So we can say that t is equal to a square into r, and we get a second order partial differential equation from the given equation z equal to f of x plus ay plus g of x minus ay. Now similarly, if we have a equation which involves n arbitrary functions, z equal to sigma r equal to 1 to n f r br, f r is a function of br for r equal to 1 to n. So where the functions f r are arbitrary and br are known functions, then we get a linear partial differential equation of nth order. We can follow the same procedure as we have done for the equation z equal to f of x plus ay plus g of x minus ay, where we have two arbitrary functions f and g, and they are functions of x plus ay and x minus ay. Now second order equations in physics. Let us see some physical phenomena and see how the second order equations originate in that. So suppose we have a we have a long insulated cable, and we are considering the flow of electricity in that. So assuming that the flow is one dimensional, the potential drop in a linear element of length delta x, okay, suppose you have a long insulated cable, okay, you take an element delta n x in this, okay, at the point x. So, then the potential drop, okay, will be equal to where where R is the resistance in the cable, L is the I is the current, and L is the inductance per unit length. So, then what will happen? We will get the E is the voltage. So, potential drop will be given by minus delta E equal to I R into delta x plus L delta x into delta I by delta T. And if there is a capacitance C and a conductance G per unit length, then we have this equation minus delta I equal to G delta x plus C delta x into delta E by delta T. Now, from the equations 4 and 5, what we do is we divide this equation 4 by delta x and let delta x go to 0. Then what we have, let delta t go to 0, then delta x also goes to 0. So, we have minus delta E by delta x, okay, equal to I R plus L delta I by delta T. So, that is this equation delta E by delta x plus R I plus L delta E by delta T, and this equation also be divided by delta x and let delta t go to 0. So, that delta x also goes to 0. So, we have delta I by delta x plus G C times delta E by delta T. Now, from the equations 4 and 5, okay, we have the partial derivative of E with respect to x plus R I L plus L times partial derivative of I with respect to t equal to 0 and partial derivative of I with respect to x plus G plus C times partial derivative of E with respect to t equal to 0. We can easily get these equations by dividing the fourth equation by delta x and letting delta t go to 0. When delta t goes to 0, delta x also goes to 0, and so we have the equation number 6. And similarly, in the equation number 5, we divide by delta x and let delta t go to 0. So, that delta x also goes to 0 and we arrive at the 7th equation. Now, from 6 we can see that when we differentiate this 6th equation again with respect to x partially, then we have second order derivative of E with respect to x plus R times partial derivative of I with respect to x plus L times partial derivative of I with respect to x and t, and then this equation when we differentiate with respect to t, 7th equation we get partial derivative second order derivative of I with respect to t and x plus G partial derivative of E with respect to t plus C times E t t, that is delta square E by delta t square equal to 0. Now, let us eliminate the partial derivatives of I with respect to x and the second order partial derivative of I with respect to t and x from the equations 7, 8 and 9. Okay. In the 7th equation we have partial derivative of I with respect to x, and in the 8th equation we have partial derivative of I with respect to x and second order partial derivative of I with respect to x and t, and in the 9th equation also we have second order derivative of I with respect to x and t. So, let us eliminate partial derivatives of I with respect to x and with second order derivative of I with respect to x and t from 7, 8 and 9 we will arrive at this equation, which is a second order equation in the variable E. So, second order derivative of E with respect to x square will be equal to L C E t t plus R C plus L G E t plus R G. Similarly, you can differentiate 6 with respect to t. Okay. When we differentiate 6 with respect to t and 7 with respect to x, okay, you differentiate 6 with respect to t and 7 with respect to x, we have this equation delta square I over delta x square equal to L C delta square I by delta t square plus R C plus L G delta I by delta t plus R G I. When we eliminate the delta square E over delta x delta t and delta E over delta x, the procedure is the same, exactly same as we have done in this case. To get the equation for the voltage E, we can get the equation for the voltage current I on eliminating the second order derivative delta square E by delta x delta t and the first order derivative delta E by delta x. Now, the equations 10 and 11 the equation 10 and the equation 11, this one are called the telegraphy equations. In the special case where the leakage to the ground is small, that is G is negligible and the frequencies are small, that is L is negligible. For instance, in the case of a submarine cable, then the equations 10 and 11. So, taking G and L to be 0, the equations 10 and 11 reduce to these equations, delta square E by delta x square plus 1 by k delta E by delta t. From this equation, let us put G and L equal to 0, G if you put 0 and L equal to 0. So, this term will vanish, okay, and this term will vanish. We will have delta square E by delta x square equal to R C delta E by delta t. And in this equation, when you put G equal to 0 and L equal to 0, what do you get? This term vanishes, okay, and G is 0, so this term vanishes and this term vanishes. So, we get delta square I by delta x square equal to R C times delta I by delta d. Now, let us take k to be R and C are constants. So, let us take k to be 1 over R C. When we take k equal to 1 over R C, then we get these equations, delta square E by delta x square equal to 1 by k delta E by delta t, delta square I by delta x square equal to 1 by k delta I by delta t, and these are referred to as one dimensional diffusion equations. So, we call them as these two equations as one dimensional diffusion equations. Now, in the case where we deal with frequency high frequency phenomena, for example, in the case of a radio cable, okay, G and R will be negligible, and so 10 and so taking G and R to be 0 in these equations. If you take G equal to 0, R equal to 0. So, this term will vanish, this term will vanish, and we will get Exx equal to Lc into ETT, and in here what we will get G and R equal to 0. So, again this term vanishes, this term vanishes, and we will get Ixx equal to Lc into ITT. Now, L and C are constants. So, taking 1 by Lc equal to small c, we can find these equations. Exx equal to 1 by c square ETT and Ixx equal to 1 by c square ITT. These are referred to as one dimensional wave equations and also called as radio equations. Now, let us take one more example where we are considering the Poisson equation for the gravitational potential. So, let us derive a simple partial differential equation of second order known as Poisson equation for the gravitational potential. Let F be the gravitational potential due to a point mass, then from Newton's law of gravitation, F is equal to minus gm Er over r square, where Er is a radial unit vector and r is the radial distance and m is the point mass, okay, mass of a point located at the origin. Now, let us suppose a spherical surface delta b of radius r centered at the point mass m, centered at the point mass m, then the total flux of the gravitational field F over the closed surface del b is this integral, the integral over del b f dot ds, which is equal to integral over del b f is equal to minus gm er over r square into dot ds. So, minus gm over r square is a constant, we can write it outside the integral. So, minus gm over r square, the integral over del b er dot er ds, er is a vector normal to the element ds. Now, er dot er is equal to 1. So, we have minus gm by r square, the integral over del b ds, and this is surface integral. So, the surface area of the spherical surface is of radius r is 4 pi r square. So, minus gm over r square into 4 pi r square, and we therefore have minus 4 pi into gm. Now, what we do is let us apply the divergence theorem. The divergence theorem is a relation between the volume integral and the surface integral. So, what we have here the integral, this one, this integral over the spherical surface f dot ds can be converted to the volume integral divergence of f dv, okay, and divergence of f, integral over b divergence of f dv is equal to minus okay, this integral we have already found, this integral surface integral we have already got, this is minus 4 pi gm. So, this volume integral becomes minus 4 pi gm. Now, f is equal to minus grad phi, and so m is equal to integral of, and m is equal to integral over b rho dB, where rho is the mass density at each point. Then we get rho square phi into m by rho. We can see here this is integral over b del dot f dv, okay, is equal to integral over b del dot f is equal to minus del square phi del dot f equal to del dot minus del phi. So, what we get? Minus del square phi. So, we will get here minus del square phi into dV, and this will be equal to minus del square phi into m over. So, integral over v dV, and this is volume. So, minus del square phi, this volume is equal to m over rho. So, we get minus minus m del square phi into m by rho equal to minus 4 pi gm, and so we get del square phi equal to 4 pi 0, which is the Poisson's equation. So, now at points external to the distribution of mass, we can imagine empty spheres centered at these points through which the net flux of the gravitational field is 0. Hence, we will have del square phi equal to 0. Net flux is 0 means we will have 4 pi gm equal to 0. So, we will get del square phi equal to 0, and del square phi equal to 0 is called as the Laplace equation. With that, I would like to end this lecture. Thank you very much for your attention.